Hello, Moses. Hello.
Hello. How's it
Hey,
going?
Michael. So, Michael, can you hear us?
Yes, hi, good morning. How's everyone?
Good. Thanks.
Good.
Good.
Okay. There's no one in the classroom yet. So,
Michael, I can see your,
my
what did,
what?
I was just about to say I could see you're a musician, Michael.
Oh yeah. Um, yeah, not so much with the piano. I play the string instruments. My fiance plays the piano.
Okay, okay.
Nice.
I always
Cool.
wanted to, but I
hmm
couldn't get my fingers to do that.
Yeah. So what string instruments do you play?
I play guitar. I played bass for a while. That was kind of
hmm
difficult for me. Ukulele. Um, I've been trying to learn the banjo, but
Okay,
the different the small string being above the big string is really screwing with me. But
gotcha, gotcha. That's cool.
do you
Nice.
play music?
Yeah, I played the violin for many years,
That's awesome.
and yeah, I've been learning the mandolin recently. Um, so yeah,
That's awesome. I always wanted
yeah,
to play the mandolin.
yeah, yeah. It's a cool instrument. Um, yeah, I'm kind of getting into some, like bluegrass or newgrass, kind of stuff.
Right.
So definitely inspired by all those, yeah, uh, the sounds of, yeah, like the mandolin and the banjo and the uh, steel guitar and just all that stuff. It's a cool sound.
Right. Yeah, I like it too. It's very cool.
Good, good, good. So, Luke, hello.
Hi.
Everybody have a good Labor Day.
I slept a lot and it was fantastic.
So did I.
Absolutely.
You're missing a couple of us, right?
But other than that, um, I didn't do much.
Yeah, I didn't do much either. I should have done more, uh, particularly school-wide. I could have used to get caught up on some things.
Yeah, that's how I feel.
Yeah.
I think most of us here, I think we're missing uh, Jordan, right? Yeah.
Burden, yeah.
So, you got my mail, I suppose, saying that I will have the midterm one take-home style. So be prepared for that. I haven't yet made the question, even though it seems like most probably it will be on finding the basis vectors for spheroidal coordinates, so hyperbolas and lines, half lines. So that's what I probably will do, but I haven't worked it out, or I should say, worked it out many years back, but not in the style that I do these days. So yeah, it should be. That's what I expect it would be on, but no promises. Okay. So there was a homework due today. So the only thing we have now is midterm one, which is on Thursday. this will be take home, right? So this will be take home exam. And it will be available, let us say, on the course webpage at class hours. That's what I plan to do. That gives me more time, right? So that's, let's say by 9:30 a.m. I will post it. And when do you make it due? I say, so this will be available at this time. And it will be due, let's say, let's make it due next class, right? So it will be like a homework. So due at 9:30 a.m. 9:30 a.m. Tuesday, right? So that will be, when is that? What's the date? So that's 17th and September 15th. But sounds reasonable. Okay, now I think we're all of us.
I'm having a little bit of internet trouble, so I may be like in and out. Hopefully,
Sure.
people outside my house working on the power lines, so it's kind of in and out. So
Yeah. So yeah, I think the recording helps in that case. Yeah. Okay. Any other comments or anything concerning the course? Okay. How did the homework go? Any comments on that?
I used a metric, and it was pretty easy using that.
I didn't understand, Jordan. Can you repeat?
I used oh, my dogs.
That's nice.
I used the metric to do it, like you said, that we could use the metric, and I found it to be easy using that. Not too bad.
That's okay. I think then you get more information out there about it. So with the vector style, it is yeah. I think the insight is there, but probably less resource out there associated with it. Any other comments? Anyone else? How did the homework go? How many could finish it? Could everyone finish it? Yeah. Michael, Luke, Alia. Okay, great. So
I did not.
yes. Yeah. But is it clear how is it to go? Like
Yes.
one point? Yeah.
Yes.
Yeah. Okay. And all of you guys use the method I suggested, or was it? Did you guys use the metric by any chance? It's okay either way.
Yeah, I used your method.
Okay, cool. So it worked out. Oh, okay, cool. Okay, good. So we will pretty much do the same thing. We will just finish this up. Basically, we have to define the curvature also, and even though we will not complete the story in the sense, then you'll build some physics out of this, which is what general relativity is, and a lot of other things like even topological insulator, which is very popular these days. That uses the same idea. It is built upon this connection and curvature tensor. So basically, I will define the curvature and do some examples, exactly like what we did in the Christoffel symbols, so that you have some experience in evaluating these quantities if you ever have to in any other context. And again, it doesn't have to be general relativity. So again, let's so today it is going to be curvature tensor. This is curvature. Usually it's a tensor. We'll define it as we research. Again, we have coordinates. Let's quickly summarize. So coordinates are UI, which means U1, U2, U3. And for reference, which is not really necessary, we have also been using the rectangular coordinates x1, x2, x3, and there are transformation between them, right? Think of cylindrical coordinates. Rho is equal, rho cosine theta is equal to x, y is equal to rho sine theta, and x squared plus y squared is equal to rho squared, basically the geometry of a right triangle. Immediately, we can define basis vectors. Which are EI is equal to change in the displacement vector with respect to coordinates UI, and that is, these are the covariant and contravariant vectors or gradient of UI. So that's a two basis vectors you can define. As a scale factor, you can define as the magnitude of EI, and you can define the line element in terms of the covariant basis vectors. And immediately we have orthogonality, which comes out to be very useful, orthogonality. And so this is I dotted with J is delta I J, and completeness is 1. This is a sum, like sum of all the outer product of the unit vectors gives you the identity matrix. From this point on, we define the metric. Metric are the components of a quantity that measures distances, local distances, and the metric tensor, which are the components of the infinitesimal distance, if you want. That's equal to EI dotted J. That's your metric. And then we define the connection. So this is what we defined last time. This has to do with how does the unit vectors change with coordinates. It is we learned this very early, but it's just that now we have a very clear definition or a collection of every unit vector with respect to every other coordinate. And for that purpose, so this time, let me define the connection itself as a vector. So this is A, I, and K. This doesn't matter, K where it is with respect to I, as we saw in the last class. And this is built out of the gradient of all the covariant vectors. In principle, we would like to know, give me all the covariant vectors, how does it change with your coordinates, which is the idea of a gradient. That's what we would like to do. But then get the components of that. And all the components are covered in the Christoffel symbols. But if we only worry about the components of this quantity, that is change in this basis vector, need not be in the direction of the basis vector itself. It can have components in all directions, and that's what we mean by the connections. So find the variation, and then its component in every other basis vector. So the vector nature here is captured by this vector. So this is the vector. So this is the vector nature. And again, when I say vector, one should be careful. Does this transform like a vector? We pointed out that this does not transform like a tensor. That means these components do not transform like a vector either. But here what I mean is that this quantity here that is taking the free index from this quantity, and it is not these two quantities. That's what I mean there. And the moment I have a vector, so for every I and a k, I will get a vector. So in principle, if we were in a three-dimensional space, there will be three basis vectors. I can take three values, k can take three values. So there are 9 vectors you can build out of this, and that's the connection. And we also said that the Christoffel symbol, which will be I, J, K, K can be anywhere. This will be equal to, just take E, J dotted with the vector. So if I take the dot product of this, this gives me all the Christoffel symbol. Again, the information content here is that how do the basis vectors change as you move along from one point to the other in a coordinate system. Intuition is if you take the radial vector as you go from on a circle, if you go from one point to the other, it changes, and how do you capture that in a quantity? So that's a connection. Again, the first derivative of a basis vector, very naively speaking, is the first derivative of a basis vector. Now we want to define what is a curvature. Again, notice the difference between the two. This is a quantity, and when you take its components, it keeps you collect all the components of this gradient of the basis vector. So these are all the components of this quantity. You can hit it from the left, and you can hit it from the right. So similarly, as a geometrical object, the curvature will be defined as, we'll use this letter here. This is a curvature. It will be this will be an actual vector, unlike connection, which does not transform like a tensor. This is actually a vector in a sense, vector with these indices. Right? So it's a tensor of rank 3 in this case, but very quickly we will make it a tensor of rank 4 if we talk about the components of this quantity. This will be simply del crossed with A. That's it. Remember that the connection itself is a gradient. So in that sense, we have developed a double gradient here, but not only double of a gradient, we have taken the cross product, which typically brings in two operators in a commuting form, if you want. So it's like going from one path to the other and then coming back from the other side. So, but as far as definition, we will look at the definition, and this is del.
So from just like a calculus standpoint, the second derivative gives you the curvature of the function.
Correct. That's correct. That's correct.
So how does this represent like a second derivative? Just a
because A has another derivative.
Oh, okay.
A has another derivative. So actually, in that context, it leads to an extra credit problem, right? I give this problem the undergraduate course. Maybe I've asked this before. So if you have a plot of x versus t, right? That's a typical plot we asked to do in kinematic equations of motion in early introductory physics program. And let us say we have so this is that's a path possible. And if I were to find the velocity of the particle, so this represents the position of the particle. So this is position and time. In a position time graph, how do you find the velocity at a certain point? Let's say I want to find the velocity at this point. Geometrically, how do you get that? All of us know this, I suppose. V is dx by dt. What kind of geometry gives me that quantity? How will I find the velocity at this point in time, let's say?
It's just the line tangent to the curve.
Line tangent to the curve, correct? So that's nice. So you just draw a tangent, which is unique for a function, and you find this to be angle theta, and slope of that tangent of theta gives you the velocity. So that's a simple way of doing it, and you can visualize that. Oh, if it was horizontal, then it is zero velocity, and as the slope increases, it's going faster and faster. In this plot, how do we get the acceleration?
Take another derivative.
Geometrically, what will it be?
The rate of change of the velocity.
Secant line.
Secant, I didn't hear the other comment.
I just said the secant line.
Secant line, can you help me with that? Explain? We are not capturing.
I was just thinking, since it's the tangent line, you can take the derivative of the tangent. So I guess that would be the secant squared.
Secant, oh, tangent theta square, but how will you see it geometrically? Yeah, that's correct. Secant, yeah, so I think what Michael is saying is that dv by dt will be d by dt of tangent theta. No, right, not secant square theta. This will be secant square theta. Then you have to do theta dot. Right? Then you multiply by theta dot also, right?
Right, okay.
So I think, yeah. So what does that represent? Yeah, that's the point. I mean, yeah, some geometrical, like slope is a geometry, like looking at the plot without doing any calculation, we get a picture of what's going on. So how do you do acceleration in a position time graph? Second derivative, right? Second derivative, right?
There is related to local, maximum local and minimum local, the second derivatives in calculus. I couldn't form it.
Yeah, but yeah, there you evaluate it to check if it is a local minima or not. Yeah. Yeah, that is a good point. But what are we checking there? Yeah, I mean, think along that line.
The curvature, is
Yeah,
it up or down?
Yeah, good point. Curvature, right? So basically the curvature of this plot at any point gives you information about acceleration. So simplistically, what you can do is that at any given point, that's a good answer, because maximum minima checks that curvature. Okay. So at any point, so for example, let's say you're here, you want to visually try to fit a circle that is tangent on that. So this is a curve, so maybe this is a circle there. If you want to fit in here, you want to have a much bigger circle, right? If you try to visualize it like that. So the curvature is related to the radius of circle that you can place next to the curve. So pick 3 points. So curvature depends on 3 points. As Khalid said, you have to go not just 1 point, that will give you a minimum, and then you have to go to the next point also. So a circle's radius is a measure of that. If that is not comfortable, just think how much it bends. Very simplistically speaking, how much it bends. Like here, the acceleration is very high. Here, the acceleration is very high. Here, the acceleration is slow. Right? So that's a way to look at it. So second derivative, so acceleration is second derivative of position with respect to dt squared. So this is related to curvature. Just the idea of a curvature. Curvature is usually inverse of the radius of a circle. Like if you have a circle of a very large radius, then it is a smaller curvature, and a small radius circle has a higher curvature. So that's sort of the idea of a curvature, and that's what you're building. But now, since remember that we had basis vectors, and we are taking the gradient, there were suddenly 27 components, right? Because each one can go in different ways. Now we are taking the second derivative. We take 3 more derivatives of the 27. So there are 81 in principle curvatures, right? 81 second derivatives you can build out of that, right? And that's correct. In principle, there are 81 components of a curvature tensor. But then people get smart for different physical quantities. You build different things, and usually this quantity comes out to be a very good measure of the curvature of a space that is built around. So this is a quantity of interest, but basically there are 81 components. Does that help roughly give an idea? And this is an extra credit problem, even though pretty much I did it, but construct the problem and answer it anyway. Right. Any questions on that? And hopefully that gives you a rough idea of what it is. I'm not trying to say that this is one-to-one related, but that also gives you a feel for general relativity, right? There is acceleration involved, but it's not straightforward as it is here. Okay.
So real quick, when you can erase it, but you mentioned like thinking about the acceleration by drawing a ball. You have to consider 2 points in t, right? Otherwise, it doesn't make sense. Like if you just
3 points in t, or 2 points in t actually, because the tangent gives you 1, right? Yeah, velocity. 3 points actually. 3 points in t gives you the because velocity actually is 2 points. So for example, if this was the curve, velocity requires that I start from the second point and you have to take the limit, right? So this is x1 t1, and that's x2 t2, and velocity will be x2 minus x1 over t2 minus t1 in the limit t2 tends to t1. Correct. So in that sense, it is 2 points.
Yeah.
Correct. And of course, at the very point, there is only 1 point coming in. But if you want to do curvature, you have to go to the next point. You have to build 3 points. Right. And again, if you think of it as velocity, you reach here, and you take it from another point and again reach there, and how the velocity changes with time. That's clear, right? If you've done numerical analysis by any chance, you will see that first you will subtract 2 quantities and divide by the ratio to get a derivative or get quantities like this, and then you have to go to the third one. So at least 3 points are necessary to find a second derivative. Does that answer your question?
Yeah, that's exactly what I was looking for.
Yeah, so 3 points, yes. And anything higher, of course, needs more. But the remarkable thing is that apparently, for most of what we see around us, second derivative does a great job. In fact, in many cases, it's exact. So yeah, so this is there are lots of second derivatives here with respect to the coordinate this time, not time. Lots of second derivatives, and that's what the curvature tensor. And this is a special set of those quantities, especially the curl specifically is a special choice of that. If I were to substitute this in there to see the second derivative in there more clearly, substitute this there, and should I? Yeah, okay. This will get very confusing now because there'll be too many vectors in there. So
I think it's helpful writing it out. I think it.
Yeah. I'm going to write it out, but I'm just warning that there will be a lot of vectors and it will be a little confusing as to what goes with what. But let's write that. So del of E I and dot it with K. And here it is still clear because this is the only free vector here, right? It is not, there is no ambiguity in here. So this gets dotted with that, and since I wrote a bracket, and then you take the cross of the whole thing. But now suppose I were to distribute this, distribute the cross product. So first I can hit this quantity, or I can hit the second quantity. Right? That's the two pieces in there. So this is equal to this way. So I can hit the first quantity, del crossed of I. So again, there is no ambiguity here. The vectors come into there, and the right component of the, like this is the Dielectric principle, so this is dotted with. Okay. That's only one piece though, so I can hit this gradient on this, or I can hit the second quantity, and here it shows out the two second derivative coming up very clearly, and there is a second piece. Now second piece, now notice what is happening. This is a cross product, so its order matters. I'm taking the cross of this with this quantity. The moment I take it inside, this vector has gone to the left. Right? So I have to change the sign of my cross product. So this is no more plus, this is my minus. Instead of saying A cross B, this has become B cross C. And this is L of EI. That's this quantity, but this has to come and hit here. And this is where I was saying it gets messy, because now there are two vector quantities in each, and one is getting crossed and when it's getting dotted. So the cross is between these two quantities. Right? These two quantities are crossed. And there was a dot between these two quantities, and that's dotted. You can bring this out using indices very clearly. But before I do that, what is this quantity equal to? It's something familiar here? curl of a curl?
That's 0.
Right? The curl of a curl is 0, correct? Unless something fishy happens in there, usually curl of a curl is 0, but there are instances when sometimes this contributes just at a whole, like Ampere's law. You have an Ampere's law. In that case, this does not go to 0 all the time. But this is typically 0 for well-defined functions. That's 0. So if we were to say this is typically 0.
So,
Yeah.
real quick, like graphically, how can you have like a curl of a circle, like a curl of a? How can you have a curl of a curl? That doesn't make sense to me. Seems like it should always be 0 because it's.
Maybe I said it wrong, right? I didn't mean the curl of a curl. I think what I meant was the curl of two gradients. That's what I meant.
Okay.
It's not curl of a curl, right? Curl of a curl will be this, right? Of, let's say, A kind of. I think I said it wrong, sorry.
Okay.
But having asked, since you asked that question, your question is still valid. If you have a curl of a field, then you take the curl again. That is perfectly fine, right? So, for example, where can we see this? Yeah, in electrodynamics, you see this. For example, del cross in electrodynamics, you will see that the magnetic field will come out to be the curl of a vector potential. Okay. That means to say that A is pretty much, sometimes actually most often, this can be thought of as is it? Yeah. Or yeah. So for example, if you have a line, right? So this is a current carrying wire, right? And we know that the magnetic field is like this. Agreed?
Mm-hmm.
The A field for this current carrying wire will be in the direction of the current carrying wire itself, and it will be the largest at the center, but it will go off. It will get weaker and weaker. Okay, so it's like a field that kind of provides it's a source of the magnetic field. If the derivative of A gives you the magnetic field. In that sense, it is. Or you can say another way of interpreting it is it's a magnetic potential. That is how it is. It is a magnetic potential. Like you have an electric potential that gives you the electric field. Gradient of the electric potential is the electric field. So similarly, you have a field A. The moment you're given a wire, usually in most of the naive scenarios, the simple scenarios, the vector field or the vector potential, you call it, is exactly in the direction of I, but now this time everywhere it fills the whole space. Okay? And the curl of that is the magnetic field everywhere. And the curl of a curl of a magnetic field, remember, is your Ampere's law.
Oh, okay.
Sort of
I got you now.
finishes the loop there. But I'm not trying to say that it gives a completely obvious picture there. So it is geometrically, it is deep in there. But remember that Ampere's law has del cross B is equal to mu naught times J, right? Either you say del cross H is equal to J or del cross B is equal to mu naught times J. So it seems like a current is a source of the curl of a field.
Well, plus epsilon naught times the change in the.
Yeah. That's the Maxwell, right? Yeah, good, very good. But this is the introductory level Ampere's law. Very good. So this is equal to D of epsilon mu naught times E, electric field. Very good, right? So either you can have a current or you can have a changing electric field. So let's say that we are in a static scenario where things are not moving, then for a moment you can stop worrying about that. But yes, in principle it is there, no doubt about that. But just to get a feel for what cross of a cross is, so that's a place where this comes that, curl of a curl quantity, where does it show up? So that's the physical quantity that is there. But having said that, I mean, I don't think I have conveyed to you exactly how it shows up. We will do this in E&M. All of you guys are there in E&M. But again, that doesn't mean that I will actually give a geometric picture very easily there. So it is there, but at the same time, it is not very trivial out there. That's the best I can. I think that would be a honest comment there. Okay, but at least you see that I can guide you into that, and from there you can take it over. Okay, helps. Okay. So this quantity, because it is this is two gradient operators coming in, it is 0. How do you prove that that's equal to 0? I think I've asked you many times probably. How would you prove that that's equal to 0? So suppose you are in a really important project and you're analyzing a quantity, and you come out and you see that there will be some very remarkable result. Something can be explained if this is not 0. So the question is, can this not be 0, or why is it 0? How would you, why should that be 0?
Could it not be 0 in like higher dimensions, or like
actually, it is much more. Even in higher dimension, it will be 0. So where is this not 0? So let's say, so this is a function, and I have two gradient operators acting on it. Let's go to the index notation that we have worked on. So this is a cross product. So this is I, J, K, and del J, del K. Right? That's what this quantity is on the left hand side. Is that very clear? Are we comfortable enough with this index notation, or should I be explaining that more?
no, the cross product gives you the epsilon ijk and the two dels, and then you have EKF is the right, the functional.
Yeah. Are others equally familiar, or at least gives, once I write it, is that clear enough? Can I proceed there? Okay, since I don't get any answers, I will assume that I'll proceed. Yeah, thank you. So notice now, use the property of Levi-Civita that if I were to replace J and K, my answer is supposed to flip sign, right? But if I were to replace J and K here, this is like replacing the derivative of d by dx with d by dy, right? d1, d2 will be d by dx and d by dy. But we said that we work with functions that are well defined, well behaved. That means to say that partial derivatives can be moved around. Right? So if partial derivatives can be moved around, but this is not, this changes sign. So the only way this can come, these are compatible is that this is 0. Like this is symmetric under swapping J and K. This is antisymmetric under swapping J and K. That doesn't get along well.
Yeah, because you get a minus. You would get a minus
Right.
epsilon I kj.
Exactly. Right. So for example, this is the way you will proceed to prove that is, or this is the same as epsilon I j k. No, I wanted to stop it, right? So this is kj, kj, dj, dk. Right? But that's the same as, because these are symmetric, that's the same as minus epsilon I kj del k del j, because that's symmetric. But then these are dummy variables. I can replace k with j and j with k, right? These are just dummy, so I replace this accordingly. And so I get I j k del j del k. So some quantity on the left is exactly equal to the negative of the same quantity on the right. Only way that can work is that that's a zero. So symmetry and antisymmetry doesn't get along. So it's just symmetry that decides that. So in that sense, in any dimensions, that will work. So that's Levi-Civita has this power. So it's pretty much permutation. Okay. So that's zero, except if the partial derivatives are not, and that happens. Like non-conservative quantities have that. But let's say that we are working with stuff where this is actually equal to zero, and then we have our curvature tensor given in terms of this. Right. Again, one should be careful about what this means. There's a so let me write both right here. So there's a cross and a dot. I don't know what's the right what's the standard notation. There is no standard notation in this. In fact, typically you don't write it in that form. Cross and this is dot. So how you will evaluate this? So if the I mean, this is when you want to write it in a very generic form. You do this. So it's good to at this point just define at least what certain things are. Let me define what is Riemann curvature. So like Christoffel symbol, where the components of the connection, Riemann curvature tensor are the components of the curvature. Okay. And how do you define that? So remember that, first let me rewrite this. If I were to write I of k, this is nothing but since it's a curl quantity in index notation, this has a component A, right? Like since these are the components of this vector. That's equal to epsilon A, B, C, and del B, and A, I, K, the connection, the C component of the connection. Right? Again, these are the Levi-Civita symbol. And Riemann tensor is defined as, this is R, I'll write the indices in a minute. So this will be epsilon, so this is sigma IKA, and multiply it with Levi-Civita symbol, epsilon A, B, C. So now since I have contracted over the A, there is only B and C remaining. So the Riemann tensor has B, C, I, and K. So it's a 4th rank tensor. So this is a 4th rank tensor. And this is a Riemann curvature tensor. And general relativity is written like we have our Newton's law. So Einstein's equation has this on the left hand side. This is a quantity in which using which it is written. And that's it. So if I were to expand this, I just have to bring this in here and put it. So basically, this is a way of writing it in component form so that I don't have to depend on this vector index. This vector index has this issue that unless it comes in the right order, it is not convenient to write. So it very quickly becomes ambiguous. This is neat. Once you have indices, you just have to follow the standard notation and it goes in very smoothly. No wonder Einstein had to come up with this, otherwise he couldn't have written it. Yes, Christian, please.
So you'd have epsilon ABC, epsilon, D, E, F.
Yes, let me write that down. I was wanting to write, but then there was no space. So let me go to the other board if you don't mind.
So then you'd have your deltas and you'd do that.
Exactly. So let me write that down. So I think that's a good thing to do. So this is RBC. It's RBC IK is equal to sigma IK, which was epsilon A. I cannot use BC because I've already used BC. So let me use B prime, C prime, and gradient of B prime and A IK C. That's your whole thing is your sigma IK A, right? IK and A, and these are all summed over B prime C prime. And then I have epsilon ABC. But as Jordan pointed out, there is an identity in here, right? There is a so this is equal to del of B prime B, del of C prime C minus of del of B prime C and del of C prime B of these quantities, B prime and A C prime. Clearly, it's either B or C and swap it. So that's equal to E. These are the oops. But these are nothing but the components of the connection symbol, which are Christoffel symbols, and that leads to P of CI K minus of, no, it doesn't matter, remember C and I is symmetric in that, right? C of K of, oh sorry, this is B, right? B of I. remember, Christopher symbol itself can be expressed in terms of the metric. So this expands out again, and you can eventually write it as two derivatives of the metric. Christopher symbol are single derivatives of the metric, and these are second derivatives of the metric. So in that sense, the curvature tensor are second derivatives of the metric. Or how about this extra credit? And this is available as a resource on the, if you make a search, you can get it. So express REC5K in terms of metric. It doesn't have to be lower quantity alone. There's a lot of, so each Christopher symbol has 3 terms with the metric. So there'll be 3 terms here, 3 terms here. So there'll be 6 terms when you write it as a metric. And that's why it is messy. It is tedious, of course, to take care of all this, but that is what is needed. So hopefully that gives an idea. Let's do a simple exercise. With the limited time we have, we calculate the curvature for a, let's say, cylinder, right? And what will be the curvature of a cylinder?
What exactly do you mean?
So suppose you were to calculate these things for a cylinder, what will you get? It turns out that this actually, in a naively speaking, you would one would think that so this is a cylinder, right? And since coordinates form a circle, one expects that this will have a curvature, correct? Second derivative of this will have a curvature. That's correct. But the curvature, the way we have defined, it is a curve and it is a special combination of 2 second derivatives. So sometimes there is a chance that it might cancel out. And cylinder is an example where even though this seems to have a curve in the intuitive sense that, oh, this is curved in the way we build a cylinder, but it's actually 0, and the way one would convince that is that, oh, so this is actually, if you were to cut open a cylinder and open it up, so it is a plane. So that's a very hand-waving argument for that purpose, but that's the, or mathematically that is what is happening. But cylinder has a zero curvature. All the components of this Riemann curvature will go to 0. All 81 components of them will go to 0, even if you were on the surface of the cylinder. So let's do an exercise here. Let's stick to the surface of a cylinder. So that's so that reduces the dimensions a lot. So let's say our space is surface of a cylinder. But this is, you might have often heard the point that a surface is embedded in a higher dimension. In this case, the surface of a cylinder is embedded in the usual 3-dimensional space. So why do you say it like that? Because the derivative of some of the quantities that we will build here, like the basis vectors, will not be on the cylinder. It will actually go out of the cylinder or out of the surface of the cylinder. And that's when you say that, okay, it depends on the other outside space also. If not, if you don't allow it to have, then it's not a well-defined space, because it's derivative of the basis vectors are not actually inside the space itself. So with that, in mind, let's proceed. So what are the basis vectors on the surface of the cylinder? Now notice surface of the cylinder, what are the coordinates, let's say? Coordinates for the surface of the cylinder?
So you're just treating it as a flat plane?
No, surface of a cylinder, yeah, if you cut open it is a flat plane, but let's say it is in terms of cylindrical polar coordinates, I'm fixing rho equal to a constant. If I fix rho equal to a constant, then it becomes a surface of a cylinder, correct?
Mm-hmm.
So I have only two coordinates left then, which is U1, U2, which are basically phi and z. There are only two coordinates left. It is basically a plane, but let's think of it in terms of phi and z. Is that very clear? Questions on that? So if that is the case, what are the eigenvectors? Basis vectors. I have E of phi, the covariant basis vector is rho times phi. That's rho times phi hat. Rho is fixed. Notice it's not a standard coordinates. Whenever there is a derivative coming in here, I have to set that to 0. E of z is z hat itself. And E of phi will be phi hat over rho. That's usual coordinates in that. And I think so. These are the usual coordinates. That's z hat. And phi hat, remember, is just for reference. Here, phi hat is minus sine phi I plus cosine phi j. Remember, the moment you write it in terms of I and j, you have to go out of the cylinder. So rho hat is cosine phi I plus sine phi j. Sorry, completeness. And let's quickly do the Christoffel or the connection, right? Connection will be A ik is equal to gradient of E of I, and then dotted with E of k. So it seems like I'll first calculate the gradient of E of I, right, and then I can get all of them. So let's, since there are only 4 of them, let's just immediately do it. A gradient of E of 1. Let's say I is equal to 5. This is equal to E of 5. Gradient itself is E of phi d by d5 plus E of z d by dz. Always the gradient operator expands out like that in general coordinates. And this is not dotted, this is a dyadic. So E of phi, what was E of phi? So that's a covariant quantity, so that's rho times phi hat. Expand that out. E phi is phi hat over rho. Rho can come out of this derivative, so I have d by d phi of phi hat plus E of z is z hat and d by dz of rho of phi hat. But nothing depends on z, correct? Rho does not depend on z. Unit vectors does not depend on z. That's 0. That's 0. this is equal to 0. What is the change in phi with respect to phi itself?
Is that rho?
That's rho, but negative rho, right?
Yeah.
Because it is inverse, so it's a negative rho. So this is, notice, so this is already, you see this point. I don't have a rho vector. On a cylinder, rho vector is outside of the surface. It is pointing, so I have to depend on some quantity that is not on the on the surface itself. So already I've gone. So that's what you mean by this is an embedded in the higher diameter. So that allows me to calculate at least a few quantities. So let's say what is A of I is phi of phi will be equal to gradient of E of phi dotted with E of phi itself. So that's phi. That's equal to minus phi hat rho hat dotted with E of phi, that is phi hat over rho. That's equal to 0. Notice rho and phi hat coming together, that's equal to 0. So there will be 4 Christoffel, so 4 or 8 Christoffel symbol in principle, but since we're writing it as a vector, they will show up as 4 quantity, right? 4 connections and 8 Christoffel symbols. So this is the first one. Second is phi of z. That's equal to gradient E of phi dotted with E of z. But that's z hat. That's equal to 0. That's equal to 0. Let me do the case I is equal to z now. This will be gradient of E of z. So that's equal to E of phi, d by d phi, plus E of z, d by dz of z hat. But z hat doesn't change with anything. So derivative of z hat with z is 0, derivative of z hat with phi is 0. So this is 0 completely. So that means to say that A of, suppose I were to do now z of phi, that's equal to 0. And A of z is equal to 0. Now this is, as I said, all the Riemann curvature is going to be 0, but all the Christoffel symbol, all the connection symbols are 0. So in this case, this is sort of straightforward, that this is equal to, so now notice, suppose this had come out to be a vector, then you just take the cross of that. So del cross of each of this quantity, right? So there will be 4 symbolic tensors there. That's equal to 0 because each one of them is 0. Is the derivative of something, if a quantity is 0, is the derivative always 0?
It's undefined, right?
And typically you ask this problem, right? You throw a ball up in the air and right on top, what is the velocity?
0.
0. What's the acceleration? Change in velocity over time?
Yeah.
Right on top.
I mean, there's no acceleration.
It's this, yeah.
There is no acceleration. Try again.
It's a constant.
It's a constant, yes, because it's 9.8, right? Minus g.
Oh, yeah, okay, yeah.
How do you say that? But that was 0. Velocity was 0. How did it become 9.8? How do you show? Like velocity is 0, so.
I mean, I understand how negative g's there, but it's outside of the.
Yeah, the point is that velocity requires the next point, right? So you have, I mean, one point is not sufficient. You have to have another point, either this side or that side. Like the same thing that Khaled was pointing out earlier, that how much ever close you go, that's not 0. The other quantity is not 0. And if it is small enough, the time is also small enough, but it will turn out that always it is minus g. Right? If you're going, since it is going with uniform acceleration, it turns out to be always a constant. That's a well-defined thing. So it's a well-defined quantity. Acceleration is well-defined. Similarly, if you were to have a current carrying loop, yeah, current carrying loop I, right? And if you had so this is the axis, agreed?
Mm-hmm.
What is the magnetic field on the axis?
0.
No, no. Why do you say it's 0?
Magnetic field on the axis?
Yeah, magnetic field on the axis, if you use this right-hand rule, they will all contribute, and they're actually in the direction of the axis itself. So that's your B. Only on the axis it is actually perpendicular. Like this would be like a magnet, right?
Well, I see what you're saying. Yeah, I got
you. The magnetic field will be like this. So, but I probably cannot ask you guys this because you guys probably are not familiar. That B actually is equal to del cross A, right? I kind of gave you a hint on that before. The magnetic field is the curl of another vector field, which is called the vector potential. If you were to calculate the vector potential on the axis, it will come out to be exactly 0. Okay, and it is very easy to calculate on the axis. By the way, before I go there, what is the magnetic field slightly away from the axis for a circular current carrying wire?
So we asked the question again.
If you have a circular current carrying wire, which is introduced in introductory level physics, correct?
Mm-hmm.
What is the magnetic field, let us say here, in this diagram here, like that spot there. What is the expression for that? Have you guys ever seen that expression in your introductory level physics?
I'm assuming so.
Is it the Biot-Savart law?
Yeah, but you can use the Biot-Savart law to calculate that. I think that's what you mean.
Yeah.
But suppose I ask you, what is expression? Like one would have thought that in introductory level, I mean, what can be simpler than a loop of current? Like current carrying wire. But recall your introductory level physics. Have you ever seen that expression?
I mean, are you asking what is the Biot-Savart for the current?
No,
like,
what is the expression for magnetic field is slightly off the axis? And the answer is that it doesn't exist. Okay? It doesn't exist in the sense that there is no closed expression for a magnetic field in terms of simple rational functions. You have to introduce special functions for that. It's called elliptic integrals. Okay, it doesn't exist. So whenever you do introductory level physics, if you notice it, go back and look at it, they will say, what's the magnetic field on the axis? That's it. And they'll stop that. And in real life, you always need somewhere to go beyond that axis. But you don't have a good expression for that. I mean, elliptic integrals are not very hard, as you will see in this course. But at an introductory level, you don't know. So you would say that, oh, let me do the vector potential, which are slightly easier to calculate than the magnetic field. And then I will proceed and then take the derivative and I'll get that. And it turns out that it is exactly 0 on the axis. So it doesn't really serve the purpose. But again, you reach the same place. So it is always given in terms of elliptic. There is an expression, but not a closed form expression in terms of nice, simple, rational functions. Right? By rational function, I mean x squared divided by y squared, those kind of things. This is given in terms of an integral. So you have to go to the computer and say that, oh, evaluate this integral, and then or Biot-Savart law involves an integral, correct?
Mm-hmm.
So that integral is not doable in the case of this scenario. So you're stuck with an integral, and so the computer has to do it. But it can be done, and numerically it can be done. So what you do is that, oh, that integral can be done, you define it as a function. Right? Whenever you cannot do something, you just define it as a function, new function. Like what is sine theta? Sine theta is a series, right?
Mm-hmm.
Like, so since that series comes so often, you give it a name and then you find properties for that function. Similarly, you come across an integral, you cannot do it, so you define it to be the elliptic integral and then you find properties. If you find 2 elliptic integrals, how do they combine? If you have 3 of them, how do they combine? Exactly like sine function. Right? That's how you will see. That's the spirit in which mathematics works.
So one quick question about the circular loop. So
yeah.
Then it looks like the curl of the magnetic field on the axis is divergent at plus or minus infinity. That's what I don't understand. Like it looks like it diverges.
When you say it is infinity, it is infinity at plus or minus.
There's no curl in the magnetic field on the axis. It just looks like it diverges towards plus and minus infinity.
It will not. Actually, curl of the magnetic field will not diverge. Only place it will diverge is on the wire. Why do you say that? It will actually cancel out. I don't know why. What's the insight that tells you that it will actually?
Oh, I see how it would cancel out. That makes sense then. I wasn't thinking about it like that. I was thinking about if you just looked at the top half of the loop, the magnetic field on the axis looks like it goes to plus infinity, right?
Oh, I see. As you go farther and farther. There will be 1 over rho there. 1 over z actually. That will kill it. Yeah, good point. Yeah. The way to look at it is that you have this del dotted with E, right? I think I emphasized in our E&M class that if this is 0 everywhere unless there is a charge, correct?
Mm-hmm.
If this is not 0, that means there is a charge at that point. Right? Same thing now. Del crossed with a magnetic field. If this is not equal to 0, there are 2 possibilities. Either there is a current sitting there at that point, or the electric field is changing at that point. And that's the only way that can happen. So usually we are not doing dynamics, at least in the introductory level cases. Even in this course, in the early stages, we are not doing dynamics. Then you know that there is no current. But later in the second semester, we'll do dynamics, and that's when it really gets rich. Then you see very nice things happening, but it gets harder also. Okay. But yeah, so what I will do is, since we are out of time, probably your midterm exam will be to calculate some curvature tensors for a space, like probably the surface of a sphere where it comes out non-trivial, or non-trivial in the sense non-zero, not trivial, it's non-zero. Right? I'll ask you to do that, or maybe the spheroidal coordinates basis vectors, something like that, something that is doable. Like whatever we did, you just have to keep following it. It will be more mechanical, so don't give up. Okay. And you can also ask me on Zoom if you have any questions on your exam, okay, any confusion. Usually if I give you the first step, it's easier to go. Okay, so feel free to meet me on my office hours, or even if this weekend you really think it's important, give me enough advance warning.
So I missed the very first like 5 minutes of the class because my internet was down. So I didn't actually hear what you had said about the exam. I saw that it said take-home exam, but when will we have access to it, and then when is it due?
It is a take-home exam. It will be accessible at 9:30 on Thursday. It will be due on 9:30 in the morning on Tuesday. Okay. So on the next class, it will be available. On the next to next class, it is due. Okay. Okay. Mm-hmm. That's all. Okay. Okay, guys.
And since it's a take-home exam, we'll be able to use our notes and stuff like that.
Yes, it is open notes, open resource. You can use internet, and even talking to each other, limited sense, it's okay. For example, you can ask each other, oh, what did he mean by this question? Okay. Don't sit together and do it, but like first steps, 2 steps, you can talk to each other. Help out each other. How about that? Take it as a homework, but don't depend on it. Restrict yourself a little bit. That's all. Okay. I think even in the homework, I don't think you're taking too much help as far as I know. But even if you're taking, that's okay. This is more of a learning exercise here. And I think I know this crowd to a certain extent. So yeah, is that clear enough? So I've made it a little vague. So restrict taking help, but at the same time, asking few things is okay.
Will we be meeting for class on Thursday?
Oh, yeah. So
I mean, I think that's the advantage of having a take-home exam, is still being able to stay on track, right?
yeah, so how about this? So let's meet on Thursday, and I can at least guide you through the exam. I won't start the complex analysis on that day. So I want to start complex analysis next, but I will keep it. I will guide you through the homework, what the homework is. So maybe for a short duration, let's meet. Is that okay? Mm-hmm. Reasonable? So that might be helpful, yeah. I didn't think about Thursday as a class or not. Yeah, that's a good point, yeah. And yeah, let me not teach. I can teach because it's just complex analysis. How many of you have seen complex analysis before? Right, so yeah, Khaled, and Michael,
sure,
and
a little
Jordan.
bit.
Huh?
I'm sure I have a little bit.
Okay, a little bit, but like for example, if I tell Cauchy's theorem, does it ring a bell?
No.
Cauchy, C-A-U-C-H-E.
Have you heard of the name Cauchy? That's all I'm asking. I won't ask you to define or state Cauchy's theorem, so don't worry.
Okay.
Have you heard Cauchy's name?
It does not sound familiar.
Does not sound familiar. Okay, Alia and Luke have seen that. Okay.
Yes.
Yeah, good. Okay. Yeah, so that's good to learn then. Yeah. So this is a very good subject to have. It's something like this. You don't see it everywhere, so it's worth spending a little time on. So maybe we'll spend 4 or 5 weeks on that, and then do differential equations and do special functions basically. Yeah, so that's roughly what the process is. So we'll start with very simple complex numbers next time. Maybe on Thursday, I'll decide what to do. If I have enough things to say about the homework, I'll do that. Otherwise, maybe start complex analysis. Okay?
Excuse me, Professor, I have
yes.
a question.
Mm-hmm.
Yes, for the homework, I used the method that you used last class. Is that what you want, or you need to us to use the matrix?
No. That is what I wanted. I think Jordan said he used another method. I think if you if you had difficulty following my method, then there is not much resource on it. Not many people do it this way. But at the same time, I shouldn't say it doesn't exist. It's just, it's hard to find out there on the internet. But using the metric, it is pretty standard.
Okay.
So
What is your method called? Like, what would you call it?
I actually don't know. I would say geometric method maybe. And it's a little elementary method maybe. Elementary method. Yeah. If you guys don't mind me calling that. Introductory level differential geometry. Very introductory level. It is not sophisticated. So yeah, introductory level differential geometry. Maybe that's what I should call it. Yeah. Okay. Thank you.
Thank you.
Thanks. See you later.
Bye.
Thursday.